Morning, Algebra 1 students. Welcome to week 4 of our distance learning. This week, if you haven't noticed yet, there is only one assignment. So that is awesome because those of you that have been working really hard, you have only one assignment, so you can focus on other classes or take a break. For those of you that are maybe a little bit behind because of just the learning curve that the distance learning took on you, you get an awesome chance to catch up. Or maybe you're someone that you are not happy with one of your quiz scores and you've already used your 3 attempts. Take advantage of this extra time, reach out to either Mr. Masonoff, Mr. Lasanti, or myself, and we can schedule a Zoom so that way we can teach you and have a little tutoring session and then unlock the test for a 4th time. All right, let's just go ahead and jump right into our video lesson this week on 0406 sequences. We're going to start with arithmetic sequences. So an arithmetic sequence is a series of terms where the same number is added each time to produce the next term. So that is the key. In looking at a sequence, it is classified as arithmetic if you are adding an integer, so that could be a positive number or a negative number. And another key fact is it says it's the same term. So that right there is why we call it a common difference, because it needs to be constant. There are 2 different formulas that we can write for arithmetic sequences. The first is recursive. So the recursive formula relies on the previous term for each sequence, and also the first term must be given. Now, right here we have our recursive formula. Let's take some notes and refresh our memories on what each part means. So the n represents the nth term, so it's an unknown number of terms. So I guess that won't go up. So n term. Then f, and then in parentheses, so sub n minus 1, that stands for, that represents your previous term because you're going back 1, you're subtracting 1. And in the recursive formula, you need that previous term to build on and get future terms. And then last but not least, the variable d represents your common difference. So in our recursive formula, we need to know our common difference, and then we also must have our previous term. All right, another type of the formula is there's an explicit formula. And this is the one that in class we used more often because it allows us to find any term in the sequence. So I can find the 10th term, the 20th term, the 100th term in a sequence, and I can do so with ease. Where if I used the recursive formula, you need to know all the previous terms. So you would have to keep adding 100 times if you wanted to find the 100th term. Where if you use the explicit formula, when we get to that example here in a moment, you can just substitute and solve. So the explicit formula is the one that is the most common, and it's used more often due to its ease. So once again, let's identify what each of these variables represent. So just like before, the n still represents our term. Now in this one, we need to know our first term, all right? We don't need all the previous ones, but the initial term is key, and that is the f of 1. That represents our first term in the sequence. And then our variable d still represents common difference. Oops. And then it's multiplied by n minus 1. So that n minus 1, the n still represents our term, but it always will be subtracting 1. The reason for that is if we look at our equation, we have the first term. So if I want to find the 100th term, I only need 99 more. So 1 less than the term I'm looking for because I always have that initial term. All right. For those of you that are visual learners like me, let's get into an example. And for this example, we will identify the common difference. We'll write the recursive formula, the explicit formula, and then we will find a term. So we have our sequence here, 4, 10, 16. Sometimes you may just be able to look at that sequence and know what the common difference is. You might be able to just automatically know that pattern. But if you don't know the pattern, we can find it by taking a term and subtracting it from the previous term. Oh, let's do that for this case. Let's assume that we don't know what the common difference is, because I'm sure some of you watching at home have already figured it out. So I can take my term and subtract it. So 10 minus 4 is 6. 16 minus 10 is 6. So our common difference is we are adding 6 every time. Please make sure that you check on more than one term because the key is that it's common, the same. It needs to be constant. If it's a changing pattern, it could still be a sequence. It just wouldn't be an arithmetic sequence. So it's arithmetic because our pattern is through addition and it is a common one. So our arithmetic sequence, our common difference is we're adding 6 each time. All right, let's write our recursive formula. All right, if I look back at my example, I don't know what term I'm finding. I'm just writing a generic formula. So I will keep the f of n. And that is equal to, and once again, it's a generic formula. So I'm going to keep the f of n minus 1 because I need the previous term. And with a recursive formula, your previous term is constantly changing because as you go down the line, you keep using the previous and the previous. So in this example, initially the previous term is 4. But then when you get your 16, your previous term was 10. And if we were to find the 4th term, the previous term would be 16. So that's why it stays f of n minus 1, because your previous term is constantly changing. And then we are adding our common difference. So we just found up here our common difference is 6. So plus 6. And that's our recursive formula. That's it. Now let's write the explicit formula, because this is the one that I would prefer to use when finding a certain term. All right, let's change up our colors here. So for our explicit formula, let's look at our example here. We still start with f of n because we're writing a generic equation. I don't know what term I'm finding yet. Then here, f of 1, that stands for my first term. Well, do we know what our first term is? We do. We look at our sequence, this right here is our f of 1. That is our very first term. So since I know that value, I want to substitute that value in. So I'm not going to write f of 1. I'm going to write the value of f of 1. My first term is 4. Then plus our d, plus our common difference, which we found was 6. And then this multiplying by the quantity of n minus 1 stays the same. Because again, I don't know what term I'm writing. This is the generic equation. All right, so we have both our recursive and our explicit formula. Now we are going to take a moment and find the 8th term of the sequence. Find f, so the 8th term, so find f of 8. So that means term number 8 is what we're searching for. We can use either the recursive formula or the explicit formula for this. If I chose to use the recursive, I would just continue on with my pattern. I would keep adding 6 over and over again until I got my 8th term. And that is a valid method. However, I prefer to use the explicit formula because I can substitute and solve, and I find that a little bit faster. Now, if we look at our explicit formula, oops, didn't mean to change that color. We have f of n is equal to 4, which is our first term, plus 6, our common difference, times n minus 1. So f of, well, my n is no longer a variable because I know what term I'm finding. I want to know the 8th term. So we will substitute 8 in for our variable n. Is equal to our first term, which is 4, plus 6, our common difference. But now instead of n minus 1, we will have 8 minus 1. Now we have an equation that we can solve. If we look at the right side, the part that we're simplifying, we, as always, need to follow order of operations. So PEMDAS. Right, P for parentheses means a grouping symbol. In this case, I do have a grouping symbol because within my parentheses, I have another operation. So those mean that they are not only multiplication, they are a grouping symbol. So that's what I want to start with. So 8 minus 1 is 7. So we have 4 plus 6 times 7. Now go down the list in PEMDAS, exponents. Don't have any in this case because it's linear. Now multiplication or division, I have multiplication. So 6 times 7 is 42. So 4 plus 42. And then addition or subtraction, which I do have. So my 8th term, f of 8, is equal to 46. And that is our 8th term of the sequence. And the sequence here is linear because if I were to graph this, it would graph as a straight line and then also, are there any exponents? No, so it is not exponential. All right, we have 2 types of sequences. We just reviewed arithmetic. Now let's move on and review geometric. A geometric sequence is a series of terms where each term is multiplied by the same number to produce the next term. So in arithmetic, it was added. In geometric, it is being multiplied. So that right there is one differentiating factor that you can use if you're trying to determine whether it's arithmetic or geometric. Just like arithmetic, we have a recursive and an explicit formula. As we go through these, I believe that you will notice there are several similarities between the forms. So recursive formula is, once again, a formula where you need the previous term. So our n, as always, stands for our term. And then f of n minus 1 continues to represent previous term. So even though your pattern, all right, you have a common ratio now instead of a common difference, is through multiplication, with a recursive formula, you still need to know that previous term in order to continue with your sequence. And then if we look here, we have multiplication instead of addition. And we are multiplying it by our R, which stands for our common, that was a bad arrow. There we go. Our common ratio. Now we have an explicit formula, because especially with multiplication, when we multiply, when we have an exponential sequence, it grows very, very quickly. Therefore, because of how large our numbers are going to get, it really is going to be beneficial for us to know how to write the exponential formula. All right, let's label our pieces here. So our exponential formula for a geometric sequence is f of n is equal to f of 1 times r raised to the power of n minus 1. So our n continues to represent our term. Our f of 1 is our first term in the sequence. We always need to know that initial value. So initial term, first term, okay? And then this time it's multiplication because it's geometric. R is continuing to be our common ratio. And this time, notice that our n minus 1 is an exponent. So in arithmetic, you multiplied your common difference by n minus 1. In geometric, you raise your common ratio to the power of n minus 1, which is what makes geometric sequences exponential, because our n minus 1 is an exponent. Okay? And the logic between behind the n minus 1 is the same as it was for arithmetic, because we have our first term. So let's say we're finding the 50th term. Well, I already have one of them, so I really only need 49 more times, which is why we always have that n minus 1. All right, let's go through an example. All right, let's go through how to write a recursive and an explicit formula for a geometric sequence. All right, here we have our geometric sequence, 8, 4, and 2. When I initially look at this, I might think it's arithmetic because, oh, if I add a negative 4, so 8 plus negative 4 is 4. But then is 4 plus negative 4 2? No, that'd be 0. So it's not arithmetic because I don't have that common pattern, but it could be geometric. Now, if it's not obvious to you what it is being multiplied by, we can, instead of subtracting, we can divide to find our common ratio. So we take our term and divide it by the previous term to determine the common ratio. So 4 divided by 8 would be 1/2, or as a decimal, 0.5. Then we need to do it with the next term to make sure it's common, make sure it's constant. 2 divided by 4 is also 1/2, so or 0.5. All right, so our common ratio is it is being multiplied by a factor of 1/2, or being multiplied by a factor of 0 and 5/10. I am going to choose to write it in decimal form instead of fraction form. The reason for that is it's a lot easier when we do our calculations in a calculator to type in a decimal than it is to type in a fraction. That is the only reason I'm using instead of using 1/2, I'm using 0 and 5/10. All right, we need to write our recursive formula. All right, for our recursive formula, if we look at our example, since we're just writing the generic formula, our f of n stays the same because it is generic to whatever term we need to find. And then just like in arithmetic, the f of n minus 1 stays the same because with recursive, you need the previous term. And as you find more terms, that keeps changing as you go. So it stays f of n minus 1. But this time it is being multiplied by, and make sure you don't make that dot big enough that you know it's multiplication and not a decimal, our common ratio, which is 0 and 5/10. If you're afraid that you may confuse your multiplication signs and your decimals, you can always choose to use parentheses for multiplication instead. All right, how about our explicit formula? Oops, that's what I get for writing too fast. All right, for our explicit formula, once again, let's look at our basic pattern here, f of n, because I'm just finding the generic one. Is equal to our initial term, our first term. Well, do we know what that is? We do. If we look at our sequence here, this right here is our f of 1. That is our initial term. So because I know the value, I'm going to substitute that 8 in. So instead of writing f of 1, it'll be substituted in for the value, which is 8. And then it is being multiplied by our common ratio of 5/10. And that is raised to the power of, so an exponent of n minus 1. All right, in this problem, instead of finding the 8 sequence, let's find the 7th term. So we are going to find our f of 7, the 7th term in the sequence. With our equation, we're going to use the explicit formula. Because again, you could use recursive. You can multiply by 5/10 until you get to the 7th term. Or if you use the explicit formula like I'm going to, we substitute and solve. So f of n, only I know what term I'm finding. So instead of f of n, it will be f of 7. Got Christmas colors here. Is equal to 8 times our common ratio, 5/10, raised to the power of n minus 1. Well, I know I'm finding the 8th term, so 8 minus 1. Now that we have substituted 8 in for all of our n's, oh, oops, I just put 8. We're finding the 7th term. Better fix that. I think copying error is a real thing. All right, always make sure you don't accidentally write the number from an example instead of the number from the actual problem. It happens. All right, let's simplify this. Let's solve it. So we need to use order of operations, PEMDAS. So parentheses. Well, in this case, my parentheses mean multiplication, not grouping symbols, because I don't have any operations going on. I don't have any addition, subtraction, exponents on the inside of the parentheses, so it's not a grouping symbol. Therefore, I can move down to exponents. I do have exponents. Now, within the exponent, this one's, I mean, it's kind of actually like a grouping symbol because I need to simplify that before I can do the exponent. So 7 minus 1 is 6. So I have 8 times 5/10 raised to the power of 6. Now I can do my exponent. And remember that it's not 5/10 times 6. It's 5/10 times itself 6 times. So 5/10 times 5/10 times 5/10 times 5/10, 5 times 5/10 times 5/10. Whew, that's a mouthful. All right. When we raise that to the 6th power, we have a pretty long decimal here. So it is 0, and we have 0, 1, 5, 6, 2, 5. Whew. And now we can go to our multiplication or division step, this case multiplication. So the 7th term of the sequence, so 8 times that decimal that we just received, is 0 and 125 millionths. Whew. That is a small decimal. We now know the 7th term of that geometric sequence. All right, before we come to a close, there are 4 examples at the bottom of this document that we're going to go through together and identify whether it is an example of arithmetic or geometric, and then what the common ratio or difference would be. All right. In the examples up above, we wrote our sequences just as a pattern. There are other ways you can write and represent a sequence. It can either be as an ordered pair, which is example 1 and 2, or as a table of values, example 3 and 4. What these do for us is it identifies the term number and the value, the input and the output. So if we look at sequence number 1 here, my x value, my input, is the term. So this is the first term, second term, third term, fourth term. And then the y value, our outputs, is the sequence, that is the pattern, okay? So the first term has a value of 5. The second term has a value of negative 15. The third term has a value of 45, and the fourth term has a value of negative 135, right? So input versus output. So if we want to identify whether it's geometric or arithmetic, we need to look at our output, our y value, okay? So all of the numbers that I have underlined are what we are going to look at. So let's see, I'm gonna just start with looking, okay, so 5, 15, 45, 135. That grew pretty quickly. So in my thinking, exponential ones, so geometric, usually grow faster. So let's try for that first. So we'll take our term and divide it by the previous to help us find that common ratio. So negative 15 divided by 5 is negative 3. Let's do it to our next set to see if I was correct and verify that it's common. So 45 divided by negative 15. Yep, that's also negative 3. And then if we check a third time, negative 135 divided by 45 is negative 3. So that means we have a geometric sequence and our common ratio is negative 3. Once you have this information, you would then be able to do like we did up above and write a recursive formula, an explicit formula, and then use that to find a specific term. All right, let's check out example number 2. Same set of directions, determine if the sequence is arithmetic or geometric, and then identify the common difference or ratio. So these are also written as an ordered pair. So remember, your x values, your input is the term. So my first term has a value of 120. My second term has a value of 95. Third term has a value and output of 70. Fourth term, 45. So to determine what type of sequence it is, we are focusing on our outputs. All right, so 120, 95, 70, 45. All right, that didn't seem to jump quite as much as the first one did. So let's see if it's arithmetic. Let's try if it is a common difference. So we take our term and subtract it by the previous. So 95, because that's where the difference comes in, minus 120. Let's see. Oh, negative 25. All right, better check and verify with the next one. So 70 minus 95. Yep, negative 25. And then the last one, 45 minus 70. Yes, it is still negative 25. So because this time my pattern was through subtraction, or technically adding a negative number, that means it is arithmetic, all right? So therefore we have a common difference of adding a negative 25 to each term. So geometric, you have a common ratio because your pattern is through multiplying. Arithmetic, you have a common difference because your pattern is through adding, and it could be adding a positive number or adding a negative number. Our last two examples, 3 and 4, our information is given to us in a table. So just like the ordered pairs, all right, when we have a table, our x value, our input, is all of our terms. And then our y value, our output, is the numbers in that sequence. So our first term is 200, second is 180, third is 160, fourth is 140. All right, now look at my values here. I'm not sure whether it's arithmetic or geometric. So one of the ways is just to try it and see what happens. So let's start off by seeing if it's geometric. So to determine if it's geometric, we take our term and divide it by the previous. So I'm going to divide here. So 180 divided by 200 is 9/10. All right, now to verify this, I need to see if it works for the next set. So again, I'm going to divide. So let's see what 160 divided by 180 is. And that is, ooh, that's a repeating decimal. It is 0 and 8 repeating. So this tells me one of two things. Either one, well, first of all, tells me it's not geometric. And then possibly it could be neither. So I know it is not geometric because when I checked for a common ratio and I did that division, I did not get a common ratio. Oh, let's try for arithmetic. So if it's arithmetic, that means our pattern is through adding. So I'm going to check for the common difference by taking my term and subtracting it from the previous. So 180 minus 200 is a negative 20. Okay, so we subtract it here. Let's try it with the next one, 160 minus 180. It's also 120, good sign. And then last but not least, 140 minus 160 is 120 again. So I just verified that by adding a negative 20, that is our common difference, which means it is an arithmetic sequence. All right, last but not least, number 4. We have months versus tourists. So again, our months, our input, our domain is all of our term numbers, and then our tourists, our output, our range, are the numbers in the sequence. All right, let's see whether it's a common difference or ratio. So right away, when I look at my range, my output, I see 10 to 20. Ooh, they added 10. Okay, see if that works. Because 10 plus 10 is 20. 20 plus 10 is 30, not 40. So right there, that means it does not have a common difference because it is not the same. And 40 plus 10, that'd be 50, not 80. So let's check for a common ratio. So for a common ratio, we take our term, divide it by the previous. So 20 divided by 10 is 2. Okay. 40 divided by 20. That's also 2. 80 divided by 40, 2 again. So this time we have a common ratio. It is multiplying by 2, so it's doubling each time. And that means it is geometric. All right, I hope that this video helps clarify some questions that you guys might have on geometric and arithmetic sequences. As always, please reach out to one of the three of us if you need further clarification or would like a small group or a one-on-one Zoom session to help answer any questions you might have. All right, thank you very much, and I hope you guys have an awesome week 4. Bye.